In this lesson, we are going to talk about recursive procedures. We define a recursive formula as a formula by which each term of a sequence is generated from preceding term or terms. If you have ever taken computer science programming, then you are familiar with the definition of recursive functions. In these definitions, every term of a sequence is defined based on the previous terms. For instance, I can say that the first term in a sequence is 1, the second term is 2, but I'm going to say that the next terms are going to be the sum of the previous two terms. For instance, the third term is going to be 1 plus 2, which is going to give you 3. The next term is going to be 3 plus 2, which is going to be 5. The next term is going to be 5 plus 3, which is going to be 8. The next one is going to be 8 plus 5, which is going to be 13, and so forth. Again, recursive definitions are very, very important, and I'm going to give you examples of these in a few seconds. Two examples in math which are using recursive definitions are factorial and Fibonacci sequences. Let's talk about factorial of a number. By definition, factorial of a number is defined first of all with the symbol exclamation. Let's say 5 factorial is written like this. It is defined as 1 times 2 times 3 times 4 times 5. Or I can say that 6 factorial by the same definition is 1 times 2 times 3 times 4 times 5 times 6. But I've already defined 1 times 2 times 3 times 4 times 5 as 5 factorial. So I can write this one as 6 times 5 factorial. And as you can see, the factorial of 6 is defined in terms of factorial of 5. In general, I can write the equation, the expression for n factorial as n like 6 times, if you look at 5, 5 is 6 minus 1 times n minus 1 factorial. But factorial has to have an ending point here, and the ending point for this definition for factorial is that we define 0 factorial to be 1. This way the definition is going to stop, otherwise this is going to continue forever. For instance, if I don't have this condition here, then I'm going to write that 3 factorial is 3 times 2 factorial. 2 factorial is going to be 2 times 1 factorial. 1 factorial is going to be 1 times 0 factorial. If I don't define 0 factorial to be 1 and stop the definition of recursion, then this definition is going to continue forever, because then I'm going to write 0 factorial is 0 times minus 1 factorial, and it goes on and on forever. So that's one of the conditions of recursive definitions. There has to be an ending point here. The next example is Fibonacci sequences. In a Fibonacci sequences, exactly like the first example I gave you, is a series of numbers where each number is the sum of the two previous numbers. Now, the only difference between this example and the first one I gave you is the starting point here. The starting point of a Fibonacci sequence is that the first two terms are 1 and 1. Now the next term is 1 plus 1, which is 2. The term after it is going to be 1 plus 2, which is 3. The next one is going to be 2 plus 3, which is going to be 5. The next one is going to be 3 plus 5, which is going to be 8, and so forth. Now, the initial process is that t sub 1 is 1 and t sub 2 is 2, meaning the first term is 1, the second term is 2. And the definition can be written as t sub n, any term, is equal to t sub n minus 1, the one before it, plus the next one before it. So t n minus 1 plus t sub n minus 2. The last thing we are going to define is a recursive sequence as to be the one that every new term is found using the previous term or terms, like Fibonacci sequence. The first example says find the first 4 terms of each sequence. We are going to do A. We know that T1 is 3 and Tn is Tn minus 1 minus 2. This means that every term is the previous term minus 2. So the first term is 3, the second term is 3 minus 2, which is going to be 1. The next term is going to be 1 minus 2, which is going to be negative 1. The next term is going to be negative 1 minus 2, which is going to be negative 3. And the last term is going to be negative 3 minus 2, which is going to be negative 5. The next example says that the first term is negative 1 over 2, and the nth term is the n minus 1th term plus 3 over 2. So if the first term is negative 1 over 2, the second term is going to be negative 1 over 2, the previous term, plus 3 over 2. Now negative 1 over 2 plus 3 over 2 is going to give us 2 over 2. Which is going to be 1. The next term is going to be again previous term, which is 1 plus 3 over 2. 1 is 2 over 2 plus 3 over 2 is going to give us 5 over 2. And the next term is going to be 5 over 2 plus 3 over 2, which is going to be 8 over 2, which is going to be 4. And the next term is going to be 4 plus 3 over 2. 4 is 8 over 2 plus 3 over 2 is 11 over 2. So the terms are negative 1 over 2, 1, 5 over 2, 4, and 11 over 2. The next example asks to find a recursion formula for each sequence. Let's consider part A. You can see that the first term is negative 3, so that the first condition for this recursion is that f1 is equal to negative 3 or t sub 1, either case. The second one is 6, and the next after it is negative 12. You can see that the pattern is every previous term is multiplied by negative 2 to get the next term. 24 is negative 2 times negative 12. So I can write that f of n is equal to negative 2 f of n minus 1. Or I can write that t sub n is negative 2 t n minus 1. So this is our recursive definition. The next question is to find a recursion formula for the graph shown here. If you look at the graph, you can see that t sub 1, which is, this is 1, so t sub 1 is here, is going to be equal to 2. T sub 2 is going to be this point, which is going to be 6. T sub 3 is going to be this point, which is going to be 10. And t sub 4 is going to be this point, which is going to be 14. Now, if you look at all the y values here, you can write 14 as 10 plus 4, 10 as 6 plus 4, 6 as 2 plus 4. You can see that every term is the previous term plus 4, except the first one is already set to be 2. So our recursive definition is t1 is equal to 2, and tn is tn minus 1 plus 4. The next example, we have a sequence given here. We know that the first term is 3. If you look at the second term, I can write the second term as 3 plus 2. The third term I can write as 5 plus 3. And the fourth term I can write as 8 plus 4. Now, if you look at these first numbers, is going to be the previous term. And this second numbers are the term number. So I can write that the recursive definition is that t1 has to be 3, and tn is tn minus 1 plus n. The next question says, Peter injures his knee in a race. He is supposed to take 500 milligrams of a medicine every 4 hours for 3 days. The half-life of the medicine is approximately 4 hours. What it means is that, as we said before, the half-life means that the amount of time it takes to have half of the medicine to be gone, or to be changed to another form. So it takes 4 hours to lose half of the medicine. Now we are supposed to make a table of values showing the amount of medicine remaining in his body after each 4 hour period. So I'm going to say the first column is 4 hour interval, and the amount of medicine left in milligram. Initially, 4 hour interval is 0, so I have 500 milligram. Then after 1 4 hour, he is going to take 500 milligram, and half of this 500 is gone, so there is only 250 left. So the answer is 750. The second hour, I'm going to have 750, half of it, plus 500. So 500 plus half, 750. If you evaluate this one, then we get 875. The third, fourth 4 hour interval, I'm going to have 500 plus half of 875. This is going to give me 937.5. The fourth 4 hour interval, I'm going to have 500 plus half 937.5, which is going to be approximately 968.8. The fifth 4 hour interval, I'm going to have 500 again plus half of 968.8, which is going to be about 984.4. The sixth, I'm going to have again 500 plus half of 984.4, which is going to be about 992.2. If we continue this one, if you go this up to, let's say, 12 4-hour interval, we will get 999.9 milligram of medicine is left. The next part of the question says, write the amount of medicine remaining after each 4-hour period as a sequence and write a recursion formula for the sequence. The sequence that we got was, initially it was 500, then it became 750, the next term was 875, the one after that was 937.5, then 968.8, and this is continuing until it gets to 999.9. And if you want to write the recursion formula, I can write that every term is equal to 500 plus half of the previous term. So every term is 500 plus half of the previous term. The next part of the question asks us to graph the sequence. Roughly, this is going to be my 4-hour interval, and this is going to be available medicine in milligram. My 4-hour interval is going to be 1, 2, 3, 4, 5, 6, and the amount of medicine, let's say 200, 400, 600, 800, 1000, and 1200 here. Now, when the 4-hour interval was 0, this is 500, which is here. When it becomes the first 4-hour interval, it becomes 750. 600 here, 750 is going to be somewhere here. Then the second one is 875, which is going to be somewhere around here. Then it's going to be 937, which is going to be around here. Then 968 is going to be very close to the previous one here. You can see that the graph goes like this one. It starts at 500 and it flattens as it goes to the right. The last part of the question says, describe what happens to medicine in Peter's body over time. As you can remember, we started with 500, then we went to 750, then 875, then 937.5, then 968.8, and this continued until I got to 999.9. This means that after each amount of medicine which is taken, which is 500, the one which is left in the body increases until it reaches to a point that it's equal to about 1000 milligram of medicine.